Hello, everyone. Welcome to our session. For today, I'm going to be focusing or we're going to be discussing about binary search tree or BST. This tree is actually a special kind of a binary tree. It's unique. It's actually unique because it has to maintain a certain property. So these are actually first is a node in the left subtree or all nodes in the left subtree shall be or must be less than to its parent node or root node, and all the nodes from the right subtree or right nodes shall be or must be greater than to its parent node or root node. So meaning to say, when we allow me to use my pen. So let's say for an instance right here. So the nodes in the left subtree is or must be less than to its parent node or root node, and then the root node shall be or must be less than to its right subtree or right node. Okay, so that's the BST property, and it must always maintain that rules or maintain that property. So let's say for an instance right here, we have an example of a binary search tree. As you can see, you can actually notice that all our nodes in our left subtree is actually less than to its parent node, which is 50. And then 50 is actually less than to its node from our right subtree. So wait, where is my pen? Where there? So it's less than to right subtree. So left the node is less than to its right subtree. So okay, so let's check. Even in every even in every subtree of a particular node, it must also follow this property. Let's say for an instance with this subtree. So we have here 17 is actually less than to 22, and 22 is less than to 23. Okay, so left node is actually less than to the node, and the node is actually less than to the right node, right? So let's say we have here let's check another property of this subtree. Okay, we have our left subtree, we have 22 is actually less than to 33, and 33 is actually less than to 41. So we have left sub 3 is less than to the node, and node is less than to our right sub 3. So as you can see, all the nodes in our left sub 3 right here are actually less than to its parent node or root node, as well as your parent node, of course, must be less than to its right node. And then also it must be applied the same rule must be applied to the right sub 3. As you can see, 57 is less than 58, and 58 is less than 60, and then 70 is less than 72, and 72 is less than 79, and then 79 is actually less than 24, and then what you have right here as the left sub 3 of this right sub 3 after on your root node is actually all these nodes are actually less than to our we call this one our node here or parent node, which is 63. So 57, 58, 60 respectively. And of course, this node right here is less than to its right nodes or right sub 3. So left node is also less than to right node and less than to its to the parent node rather, and less the node or the parent node is less than to the right node. So that is why binary search tree is actually a unique property of a binary tree. I mean, a unique kind of a binary tree. Okay, so a binary search tree, the same with binary tree. It's every node holds data, item, value, which is actually called a key. And for all the nodes or for any node, X, all the keys in the left of that tree is going to be less than or equal to the key of an X, which is actually I have discussed earlier. And then for any node X, all the keys in the right subtree of X must be greater than the key of X. So that is actually the property that is going to be maintained by a binary search tree. Okay. So if we get to compare that to binary tree is just going to insert a node uh, in level order. But this time, a binary search tree is going to follow a certain property once you get to insert a node to your binary search tree. But before that, let's have the applications, or what are the applications of binary search tree. So binary search tree are actually mainly used in many search applications where data are constantly entering or leaving, such as map, sets, and most programming languages, or as libraries in most programming languages. It is also used for Unix kernels for managing virtual memory areas, or VMAs, and it's used for indexing and multi-indexing in database applications. In fact, binary search tree is actually applied as an index key, particularly in when we talk about um, indexing in binary search, indexing in creating database, or something like creating a key in our, or uh, something like creating a key for that particular table in our database table. Okay, so these are the operations of binary search tree. So you have insertion. So the same with binary tree. There are you can insert data or item or node to a tree. You can also search or search or find a certain node from a tree, and then you can also perform traversals, level order traversals, in order traversals, post-order traversal, and pre-order traversal. And of course, the deletion, which has actually three cases in terms of we actually follow the keyboard algorithm in deleting um, a certain nodes from our binary search tree. And there are actually three cases we need to understand. So again, these are the operations of a binary search tree. So let's say we are going to search element or search a node in a binary search tree. To actually search for a to search for a node, all you just need to do is um, using a recursive or looping or recursion, you can actually visit first the node, which is actually your root, and then after that, if that node or that value is actually if a node that is going to be searched is equal to the root, return that node. Okay, that then if that node that is going to be searched is less than to the root, you need to go to the left. Okay, if the node is that is going to be that is going to be searched rather is greater than the root, then you go to the right. So let's say for an instance, um, you repeat this step, comparing b with or comparing n with the new node we are at, and then repeat until either the node is found, or when we reach a non-existing node, or something like a node that points to null, or something like it's actually a leaf. Okay, all right, so let's say for an instance here we are going to find 57. So where is 57? So first is you have here 57 as the node. Okay, this is the new node to be searched. So 57 is going to be compared. So let's say is 57 is less than 50. So is 57 less than 50? That's actually false. Therefore, you will need to go to the right side because 57 is actually greater than 50. Therefore, you go here, right? So is 57 is greater than the node 63. So, or either depending on what relational operator you are going to use, all you just need to do is determine which one is the highest or which one is greater. So let's say for an instance, is 57 is let's say less than 63. That's actually true. Therefore, you will need to go here, and then um, is 57 less than 58? That's actually true. And you will need to go or traverse to its left node. So this time is 57, okay, is equal now to 57. That is true, then therefore you have just found the node 57 in that binary search tree. So that is what the algorithm is actually do. No? I mean, that is um, following this three algorithms. All right, another one is let's say we are going to find 69. So we now then get to compare the value of n, which is, let's say this is 69. Is 69 less than 50? That's actually false. So you go to the right side or something like depending on your depending on what you use. Let's say 69 is greater than 59. If it's true, you go to the right node or right subtree. So let's say, yeah, we go here. So 69 will be compared to 63. That's 69 is bigger than 63. So therefore, you have to go to the um, the right side or right subtree because again, it's greater than, saying that considering that the property of a binary search tree is that sa ganito, we have left node should be less than to the parent node, and all nodes should be greater than to the right node. Sorry, less than to the right node. So therefore, every time you compare, every time a node that is going to be searched is greater than the node, so you go to the right side. So right here, 69 is going to be compared to 72. So the evaluation is actually yeah, is 69 greater than or depending on your preference. Let's say 69 is less than 72. That's actually true. Therefore, okay, it will actually go right here. And then, as you can see, you have here, it's now deadlock. So you will now then compare 69 to 70. So which one is bigger? Of course, bigger is 70 kaysa kay 69. But this time, this value right here is actually points to nothing, meaning it points to null on its left subtree and right subtree because this is actually a leaf. Okay. Then if that is what will happen, then that node is no nowhere to be found in the binary search tree. Now, as you can see, in terms of searching a node into a binary search tree, it is actually faster. It's actually faster or efficient because it knows where to go rather than visiting each node in that particular sequence of nodes. Just like in linked list, where you are actually going to traverse each node from the beginning up to the end until the a node is found. But if it's not found, you just wasted a lot of memory because once it's not found, you just traverse from the beginning going to the end, but only to find out that that node is actually not being it's not actually found uh, in that particular nodes, no, in that particular sequence of nodes. But in terms of searching a node in a binary search tree, there you don't have to visit all the nodes because there are cases that you will need to compare each node, and then once it is less than, you go to the left. Once it is greater than, you go to the right. So left, if it's less than, you go to the left. If it is right, it's greater than, you go to the right. You go to your right. Okay. So meaning to say, all the nodes are not visited. Okay. How about if we are going to insert a node? So let's say for an instance, we are going to insert a node and then using the tree, P or tree, of an object of tree, let's say for an instance, you just have to search for the position of the n as if it is or if it were in the tree. If not, then the position is the left or right child of some node x. Meaning to say, upon insertion, let's say for an instance, you want to insert a node. Let's say we are going to insert 45. Okay, so node that particular node should be or must be the parent node. Okay. Now, let's say you are going to insert 70. So to maintain its property, so 70 will get to be compared into 45. So since it's greater than 45, um, it must be looked at. It must be placed right here. So 70 must be placed right here. Now, if you are going to insert, let's say, another node, let's say 30, so 30 is going to be placed right here because the less than the parent node. Okay, because that's the property of a binary search tree. Let's say you are going to insert another one, let's say 12. So 12 will be compared to 45. Is 12 less than 45? That is actually true. Therefore, going to the left is 12 less than 30. So therefore, it must be on the left, as this would be, or this must be the left child of this parent node, which is 30. Let's say for an instance we are going to insert 15. So 15 will be compared to 45. Yeah, that is actually less than to 45. 15 is actually less than to 15. Therefore, it will go here, and 15 is not less than, or it's actually greater than 12. Therefore, 15 will be placed right here. Now, in other, let's say for an instance, again, we are going to enter or insert another node, let's say 85. 85 is greater than the parent node, therefore it goes here. And then 85 will be compared to then this node, current node, which is 70. Is it greater, is it, is 85 greater than, or then is the new node greater than the current node or this node? Yes, therefore it will, or it must go here, and then it will be put right here. So let's say we have 100. So 100 is greater than 45, so go to the right. 100 is greater than 70, go to the right. 100 is greater than 85, therefore go to the right. All right. So in that case, the node in a binary search tree is going to be positioned in a specific or a certain position following the property. Again, all the left nodes shall be less than to the right, to the parent or root node, and then all the nodes or the parent node must be greater than the right node. So again, all these nodes right here are less than to the parent node, and the parent node is actually less than to its right nodes. Okay, if we are going to, let's say, um, what is the possible node right here? Could be a 50. Okay, so let's say we are going to insert 50. So 50 is compared, so it's greater than 45. It's less than 70, so 50 should be placed or should be stored right here. All right, so that is how you insert a node to a binary search tree. Okay, so this is also, the illustration of a binary search tree, considering that you have this already a binary search tree. So as you can see, all nodes right here on the left, on your left subtree are actually less than to its parent node, and then all the nodes in the node in the parent node is actually less than to our child node. Let's say for an instance, we are going to insert 25. So 25 will be compared right here. So 25, that's actually true. Therefore, 25, go to the left. So 25 is less than 33, go to the left. Is 25 less than 22? Since it's greater than 22, therefore, uh, let's have right here. And then since 25 is greater than 22, therefore it goes to the right side. And then since 25 is greater than 23, therefore it must be placed right here. So after inserting 25, your 25 is going to be the right child node of parent 23. All right. So how do we delete a node from a binary search tree? So when we get to delete a node from a binary search tree, you are going to follow a what we call keyboard deletion algorithm. So to delete a node from a binary search tree, It's actually a little bit, there are actually cases you need to follow because it's a little bit difficult and complicated. So basta you have to make sure that the resulting tree after the deletion is a binary search tree. So when that in our next discussion, we are going to focus on the deletion of a binary or deletion of a node from a binary search tree. But to give you an idea of how we are going to actually delete a node in binary search tree using a keyboard algorithm, it actually distinguishes three cases. So the first, when a first node has no subtree or actually a leaf, so you just delete it directly. When a node has only one subtree, when there is only one subtree on it, so you just have to take this child replacing the parent node. So either left or right. So the same way happens right here. If that node has a right subtree, a right node, then you just have to take the child node and replace the parent node. For for the nodes with two children, okay, so that is the time you will need to follow a this because this one is a little bit complicated or a little bit difficult. We'll need to follow or we'll need to follow some method which are finding the successor node and or either predecessor predecessor sorry predecessor, that is this one is C ha, predecessor because na my pen tab is not working in Mac OS. So it either you find predecessor node and uh, successor node. And then after finding either successor node or predecessor node, you will take that successor node replacing the node to be deleted. And once it is now copied, then it is now safe to delete the successor node. Okay, so meaning to say, you actually replace the successor node, you actually replace the node to be deleted with the successor node or either predecessor node. In our next topic, we are going to discuss that. We are actually going to focus on that particular topic, deletion or how to delete a particular node in our from our binary search tree. All right, so I guess we call it a day. So thank you guys for joining in. Have a great day. Bye and thank you.